Congratulations, nerds, you made it to the last lesson of the year. This is it. We're finishing it up. Today we're going to be talking about some applications of trigonometry. And these aren't serious applications, they're just kind of basic applications, all right? And a lot of it you've already learned in geometry. We'll start by talking about some basic vocabulary and structures of circles that you should already know. I've got them in this image and I've got them listed out. You should already know what the center of a circle is. It does not need explanation. It's the center. The radius, that is the distance from the center to what I'm calling the quote-unquote edge of the circle. A chord is any line segment that begins and ends on the edge of the circle, and that includes the diameter. It's not in the image because we're not doing anything with the diameter today, but the diameter is a chord. Okay? An arc. An arc is any piece of a circle's quote-unquote edge. It's just a piece of it. Cool? Now, a sector is also a piece of a circle, but it's specifically a pie slice, let's call it a wedge of the circle. And it is formed by two radii, and what we're going to, and an angle in the middle. We'll call that a central angle because it's at the center. And lastly, a segment of a circle is what you get when you slice along a chord. And, you know, this piece that comes off is a segment. So you should already know most of that vocabulary. Cool with that idea? You've seen most of those words before. So this is an arc. It's a piece of the circle's edge. This is a sector. It's like a slice of the circle, like a pizza slice or a pie slice. Cool? Cool. Awesome. Something you should already know is the circumference of a circle. Basically, its perimeter. And the formula for it, circumference equals 2 pi r. And the reason why you should already know this is because you learned about it in 7th grade math, I hope. And then last year in geometry, you talked about the length of an arc. And since the arc is just a piece of the edge of a circle and the length of the edge of the circle is the circumference, the length of the arc is literally a piece of the circumference, which is what you see right here in this formula next to degrees. It says arc length equals theta over 360, some fraction of a circle's circumference. That's a formula that you learned in geometry. It's in degrees. But we've now learned about radians. How many degrees is 2 pi radians? 360 degrees. That means that this 2 pi and this 360 cancel each other out if you're working in radians. And all you're left with is this theta and this r, which is the formula that you see right here. So the formula for arc length is much easier in radians than it is in degrees. In radians, it's just r theta or theta r, whatever you want to say, one or the other, it doesn't matter. You need to know that formula. You need to know this formula. You need to know them both. I'm going to predominantly work with this one just because radians are easier to do. But if you forget the formula, then you could always rely on this. Or if you forget how to convert between degrees and radians, you could always rely on this. My only caution to you about that is you are not going to have a calculator on this upcoming test, which means unless you're really good at reducing fractions, you're going to want to definitely be able to convert between degrees and radians and use the radian formula. But there it is. Arc length. We have a sector with a radius of 12 and a central angle of 3 radians. You don't need the picture, but if you wanted to draw one, you know, it's looking like this. We got a 3 radian angle and we got a radius of 12. Well, you want to memorize the formula? Write it every time you're going to use it. Length is r times theta, as long as it's radians. And this is radians. Literally 12 times 3. There you go. The length of that arc right there is 36. No trickery here. It's that easy. Hardest part about it is, do you know the formula? R theta is your friend. Questions about it? No? All right. What about the arc length of a sector that has a radius of 9 and a central angle of 30 degrees? You don't need to draw it just because it's just r theta as long as it's O in radians. Oh, 30 degrees is one of our special ones, isn't it? You should already know what 30 degrees is in radians. What is it? It's pi over 6 radians. So this is a pi over 6 central angle. L equals r theta. Our radius is 9. Our theta is pi over 6. 9 pi over 6, which reduces to 3 pi over 2. That is not the angle 3 pi over 2. Don't get those confused. This is length 3 pi over 2. Whatever that number is. I'm not really sure what that number is. Again, I hope you think it's really easy, and I hope you think that the hardest part is knowing the formula. So what if we take it up half a baby step in difficulty? This one, we know the central angle is 60 degrees, and we know the length of the arc created is 15 pi. We don't know the radius, so we're going to find the radius. Fill out what you know. L is 15 pi. R. And theta is not 60 degrees because that's degrees. I need radians. So what is 60 degrees in radians? Pi over 3. I can isolate my radius with one algebraic step. How do I get it alone? Well, if you divide by pi over 3, that's the same as multiplying by 3 over pi. There we go. Multiplying by a reciprocal will cancel every part of every fraction. But on the left side, and I don't use it often enough. Break out the yellow pen. On the left side, the pi's cancel, and you're just left with 3 times 15. So that radius is 45. Be in the habit of writing the formula every time you're going to use it, and you will have it memorized, guaranteed. Choose not to write it down every time you use it, well, you're rolling the dice. Are there any questions I can answer about finding the length of an arc? None. Good, because it's easy. Not good because I don't want to answer questions. Good because it's easy. Old knowledge for you. The area of a circle is pi r squared. Since a sector is a wedge of a circle, it should make perfect sense to you why the formula for the area of a sector that you learned in geometry is theta over 360 times pi r squared. It literally says a piece of a full circle's area. But if 2 pi from the last box, if 2 pi radians was 360 degrees, it should make perfect sense, and you already know this, that pi radians is 180 degrees. And what is 180 over 360? 1/2. That's why there's a 1/2 in this formula. So in radians, the area of a sector formula is 1/2 theta r squared. Know it, love it, use it. And in case you don't know it, love it, use it, also have that one under your belt as well. You learned that one in geometry. Theta over 360 times pi r squared. I just prefer 1/2 theta r squared. Radians is where it's at. Using the formula, we know the radius of a sector and we know the central angle is 4 radians. Area is 1/2 theta r squared. As long as we are in radians, we are in radians. Our area then is 1/2 for 12 squared. So like I said, you're going to be doing this without a calculator. You should be able to do this kind of math without a calculator. What is half of 4? 2. And what is 12 squared? 144. You're supposed to have those numbers memorized. Now just double all 3 of those digits and you're finished. 288. That is the area of that sector. Just like the other page, I hope that you think the hardest part is knowing the formula. You can only use this formula if you're in your radians. This says 40 degrees. We have a radius of 9 and a central angle of 40 degrees. We want to find the area of the sector. Your options are use this formula or convert to radians and use that formula. And I'm going to tell you that you must be able to convert to radians to be successful in your test. It was the very first thing I taught you in this chapter. So we might as well convert our 40 degrees to radians. If you're trying to convert to radians, then you want radians on the top of the conversion fraction, pi radians. And if you're trying to cancel out degrees, then you want degrees on the bottom of the fraction, 180 degrees. This is the conversion fraction. The degree symbols cancel out, and you're left with 40 pi over 180. I mean, you could just divide both the top and the bottom by 10 right now. And then you should be able to easily reduce 2 pi over 8, or 4 pi over 18 to 2 pi over 9. Just divide the top and bottom by 2. I'm not going to lie, I have my pi over 9s memorized. It's 20 degrees. It's just convenient. 1 pi over 9, 20 degrees. 2 pi over 9, 40 degrees. 3 pi over 9, that's pi over 3, 60 degrees. 4 pi over 9, 80 degrees. 5 pi over 9, 100 degrees. 6 pi over 9, that one's special, 120 degrees. That's 2 pi over 3. See, but the over 9s, they work nicely. They're easy. So either know how to convert or know that formula. But I can tell you one of your test questions is, what is this angle in degrees? And I give it to you in radians. You just need to be able to convert. That's one of the test questions, a conversion question. Now that we have our angle in radians and we have our radius, I say we track down the area, 1/2 theta r squared. Our theta is 2 pi over 9. And our r is 9. 9 squared. You know 9 squared is 9 times 9, right? You don't need a calculator to figure out what this equals. Because this 2 cancels this 2, and this 9 cancels this 9. What you get is 9 pi. No calculator needed. Ta-da! Can I answer any questions? Everything's very straightforward still, correct? Awesome. Are they always going to be that simple? Of course not. You know I'm going to challenge you. I'm telling you the area of a sector is 12 pi, and the length of its arc is 2 pi. Using that knowledge, we're going to solve for the radius and the central angle. If you would like to have a picture, I guess you could just slap one together right quick. It doesn't really matter much. Pictures are not drawn to scale. They never are. What we have here is an area of 12 pi and an arc length of 2 pi. I did area in blue, so I'll do all my area work in blue. And I did arc length in red, so I'll do all my length work in red. Sector area is 1/2 theta r squared. The only thing I know about that is actually A is 12 pi. That's everything I can do with area right now. Arc length, r theta. The only thing I could do with it right now is I could substitute 2 pi in for L. Oh, look, I have two equations in two variables, known as a system of equations. And solving systems of equations is something you started learning how to do in Algebra 1. The two methods you learned for that were, well, I guess three because you learned how to solve by graphing. But the two methods that you really learned to do algebraically would be elimination and substitution. Which one do you think we should try? Substitution is going to be the way to go. Why? Because our variables are multiplied to each other. That's why. You only try to do elimination if your variables have pluses and minuses between them. We're going to need to substitute. There's several ways of doing it. The easiest way that I see is getting theta alone right here, and then getting whatever theta equals, whatever the expression is, and putting it right there. That's how I would do it. So for this one, let's get theta alone. Divide both sides by r. We now know an expression for theta is 2 pi over r. We could take that expression for theta and we could put it right there. Since I'm combining blue and red, I'm going to write in purple. Theta is 2 pi over r. And then I have an r squared. Are you with me so far? Everything I've done is cool so far. Okay. These 2's cancel each other. And there are 2 r's on the top here. So this r cancels one of the 2 r's here. All that's left on the right side now is r times pi. I have 12 times pi equals r times pi. Gee, I wonder what r equals. 12 it is. You could divide both sides by pi, or you could just see that 12 is the obvious answer. All we need now is theta. And by the way, in order to find theta, all we needed to know is what r equals. So I'll take this formula right here, and I'll replace r with what we know r to equal, and reduce that fraction. So knowing sector area and arc length allowed us to find our radius and our central angle. So we haven't done any trig yet, have we? Unless you consider radians a skill from trig, we haven't actually used any applications of trigonometry. But I'm hoping you're seeing that radians are more convenient to work with than degrees. But on the next page, we're going to see an... Is it the next page? Area of a triangle? I'll come back to it if you need to see it, okay? Lucy, I'll come back. Area of a triangle, an actual application of trigonometry. You see, the only formula that you know for the area of a triangle is 1/2 base times height. And let me remind you what it means to be a height in geometry. A height is always perpendicular to a base. So if I wanted to know the area of this triangle from geometry, I would had to have dropped, and you don't need to draw this, a perpendicular height. And I would have needed to have known its length. And then I could have done 1/2 this length, which is base, times this length, height. But what if you don't know it? If you don't know the length of the height, then what you could do is you can use trigonometry and this formula here to find the area. This requires you to have the knowledge of a side, an angle, and then a side. Do you remember talking about side, angle, side in geometry? If you have side, angle, side, you could find the area of a triangle. That's not something you learned in geometry, correct? How to find the area of a triangle using side, angle, side? That wasn't a geometry skill, right? Okay, I didn't think it was. Well, the general formula is 1/2 AB sine C, where lowercase letters are side lengths and an uppercase letter is an angle. And these letters are generic. It doesn't have to be side A, side B, and angle C. It literally just needs to be any two sides with the angle between them. It needs to be the side, angle, side setup. And the angle between two sides, vocabulary for that is the included angle. That's what we say. So you say, I need to know two sides and the included angle. You know two sides and the included angle? Then you could do area of a triangle, 1/2 AB sine C. And this works in degrees or radians. You just make sure your calculator's in the right mode if it's a calculator question. Cool? 1/2 AB sine C. Just like the other formulas, if you would like to memorize it, it'll be a lot easier if you just write it every single time you're going to use it. So I'm going to find the area of this triangle. I need you to recognize that so here's what it is. I'm going to find the area, 1/2 AB sine C. But the letters A, B, and C are generic placeholders. They are not specific to any one set of sides with the included angle in the picture. It's any two sides and the included angle. So the letters don't actually line up because I'm using sine of angle B. I'm using side length A and side length C. But rather than write a new formula, just understand what the formula says. Two sides and an included angle. And then fill out the formula. 1/2, 11 times 15, sine of 28 degrees. We will grab a calculator, we will get this answer, and we'll round it to 2 decimals. My calculator is in degree mode, but in case yours isn't, press DRG, and then use left and right until you've highlighted degree and hit equals. So we're all in degree mode. 1 divided by 2, parentheses 11, parentheses, parentheses 15, parentheses, sine of 28, close sign, get an answer, round it to 2 decimals, about 38.73. And I was just about to say, and it was at this point in period 1 that someone asked me, but we're not allowed to use calculators, so this won't be on the test, right? And I was like, wrong. It will be on the test, but you're correct about not being able to use a calculator. This is one of our special angles, isn't it? There we go. So we're going to be able to find the area of this triangle using trigonometry without a calculator because that's a special angle. Area is 1/2 AB sine C. Uppercase letter tells you that it's an angle. That's 1/2 of 5 times 6 times the sine of 60 degrees. $60 degrees is in quadrant 1. I don't have my unit circle memorized, so throwing together a quick little reference triangle for myself. Across from a 60 and a 30, 60, 90 will always be a root 3. Next to it will be a 1, and there'll be a 2 right there. Sine is y over r. What's 5 times 6? 30. Half of that is 15. So I have 15 times y over r, root 3 over 2. The exact area is 15 root 3 over 2. No calculator needed. What's up? Oh, I thought you were making a comment about that. Care to ask me any questions? Also, something else that could have been a test question. What if this wasn't a 60-degree angle? What if I said it was 50? I could have said find an expression for the exact area of the triangle. And the answer would have been 15 sine of 50 degrees. That's an exact expression. Do we know what sine of 50 degrees is? No. But we do know that the area would have been 15, wrong fifth word, 15 sine of 50 degrees if that had been a 50 instead of a 60. And that could have been a test question. So instead of asking what is the area, I could ask for an expression for the area. Okay. Find the area of the obtuse triangle. Wait, does that say find the area? Okay, this is not supposed to say find the area. It's supposed to say the area. The word find shouldn't have been there. Sorry. The area of the obtuse triangle is 24. Find the measure of theta in radians. You know we're going to be using that area formula, right? Area equals 1/2 AB sine C. We know that the area is 24. We know the two sides are 12 and 8. And you're not going to have a calculator, so rather than trying to figure out what 12 times 8 is and then cutting that in half, why don't you do half of 12? What do you get? 6. So this actually says 6 times 8 times sine of C, and Trenton already said 6 times 8 is 48. Get sine of C alone. Was it Trenton or David? Oh, okay, so I said the right name. All right. Divide both sides by 48. Sine of C equals 1/2. And it just so happens that 1/2 is a value of sine that we can get from one of our special right triangles, isn't it? Where can sine equal positive things? Only quadrant 1? Quadrant 1 and 2. This is not a sine inverse question. If it was a sine inverse question, we'd be dealing with quadrant 1 or -1, and obviously quadrant 1 would be where the positives would come from. But if you recall back to the very first extra credit I gave you, your job was to find all of the angles where these kinds of statements were true. Sine is positive in 2 quadrants, 1 and 2. And let me ask you, which of those 2 quadrants gives me those angles? Obtuse angles. What do we know about the word? What does obtuse tell us? Greater than 90. So which quadrant are we in? Quadrant 2. This is where I'll find my sine values of 1/2. What's the size of the reference angle? 30 degrees. 30 degrees in radians is pi over 6. So I am a pi over 6 before pi, making my angle what? You can say it louder. 5 pi over 6. Because I am a pi over 6 before pi, I am at 5 pi over 6. You know what's really interesting about this? That means there's an angle in quadrant 1 where I would have had the exact same area, a pi over 6. This angle could have been 30 degrees or 150 degrees. Either way, the area of this triangle is 24. So there's an acute version of this triangle and an obtuse version of this triangle that have the same area. Isn't that neat? I mean, I think it's neat. I think that's pretty cool. Yes? Shh. We know it's 30 because we knew that 1 and 2 were the y and the r, because 20, it reduces. So if this is y, this is r. That makes that a root 3, but because I'm in quadrant 2, it makes it negative. That means this must be a 30, 60, 90 triangle. And the 30 is always across from the 1. So apart from the formulas, have we done anything remarkable today? Nothing scary, right? All right. Time to put the stuff together that we've learned today. This shaded thing is a segment, like I said at the very beginning of the lesson. And since we now know how to find the area of a sector, and we know how to use trigonometry to find the area of a triangle, all we have to do is subtract to get the area of this segment. This formula says find the area of the sector and subtract the area of the triangle. I hope that that's common sense why that works. But Mr. M, this doesn't say 1/2 AB sine C. You go, oh, but it does. Because A and B are just side lengths of your triangle. And the side lengths of your triangle are both the radius. So it's actually 1/2 RR sine C, which is going to be theta this time. So do I have this formula memorized? Nope. I know that formula, and I know 1/2 AB sine C, and it's obvious that if I subtract, I'll be left with that little thing. So that's how I always do it. I find the area of the sector, then I find the area of the triangle, and then I subtract. Every single time. I don't do this formula. Okay? But does that make sense, how we do that? Find the area of the pie slice, and then subtract the triangle, and all you're left with is like the crust, right? Cool. Then let's do it. A portion of a circle with radius 8 is shown. Find the area of the segment. That means the shaded thing. Round to 2 decimals. But you know what we're going to do? We're going to pretend this is my test. We're going to find an expression for the exact area. Then we'll grab a calculator and type it. Oh, 40 degrees. We just did 40 degrees. That was 2 pi over 9 in radians. We just did that one. So we don't need to redo that. We could see that from previously in the notes. There. Area of a sector. And this is how I show that area of sector. I do a subsector. 1/2 theta r squared. I'm in the habit of writing my formulas every time I'm going to use them. That's how I never forget them. 1/2 times 2 pi over 9 times 8 squared. The 2's cancel. And everybody in the room knows what 8 squared is, right? 64. The area of the sector is 64 pi over 9. That's the exact area of the sector. Now, area of the triangle. 1/2 AB sine C. But remember, both sides of the triangle are 8 because they're radii. So that's 1/2 of 8 times 8 times sine of 40 degrees, or 2 pi over 9, right? What is half of 64? 32. So the exact area of this triangle is 32 sine of 2 pi over 9. Or 32 sine of 40 degrees, whatever. This formula doesn't care if you're in degrees or radians. It just doesn't care. So what's the exact area of the segment? It's the 64 pi over 9, the area of the whole thing, minus the area of the triangle. And again, if you're going to use 2 pi over 9, keep your calculator in radians. If you're going to use 40 degrees, put your calculator in degrees, because this doesn't matter if you're in degrees or radians. So this is the exact expression for the area. Our 2 decimal approximation is, boop, right here. 64 pi divided by 9 minus 32 sine of, my calculator is still in degree mode. I'm just going to type 40 degrees if you don't mind, because I'm in degree mode. I mean, I could put it in radian mode and then type 2 pi over 9, but why bother? And I'm going to hit equals 1.77. That is a very small area, and that shouldn't be surprising. The triangle takes up most of the area of the sector. Yes, ma'am.
So on the test, we're just going to be finding the expression?
Some questions are finding expressions, some questions are finding the actual numbers, but they've been designed in a way to make sure that you can do it by hand. Either using very specific angles or very specific side lengths and things like that. Okay? So on the test, everything can be done without a calculator. That's the answer without the calculator. No. 64 pi over 9 minus 32 sine of 40 degrees, or 32 sine of 2 pi over 9. That's the exact answer. This is the decimal approximation to 2 decimals. So when you're looking at your homework, it says find the exact answer and the decimal approximation. It's because I'm expecting to see this work. I'm expecting to see found exact, wrote an exact subtraction, and then got a decimal answer. That's what I'll be looking for in the homework. And this last question says a regular hexagon is inscribed in a circle of radius 4 as shown in the image. We're going to find the exact area of the shaded region. Then we will get a decimal approximation. And I would like to, and I'm glad it's on video too, that way nobody will be able to say I didn't say it. Your homework, the next to last question, is a question like this. Is that number 10? It says it's a regular octagon inscribed in a circle, right? I forgot to say what the radius is on the homework. You need to know. The radius is 2. And for the people that are not paying attention and are on their phones, they've missed that knowledge. Okay. Anyway. Radius of 4. How can I figure out the shaded area? Be waiting for one of you to give me an idea. When you say one portion of it, what do you mean? One wedge, one sector? So that means I need another radius, don't I? You didn't low-key do this in geometry. You did do this in geometry. Except for you didn't know 1/2 AB sine C in geometry. The area of a regular hexagon in geometry? You found the area of a regular hexagon in geometry using the formula that had to do with the perimeter and the slant height. Or you used the apothem, which sounds like the word opossum with a lisp. Apothem. That's the vertical height from center to edge of the hexagon. It's called the apothem. I was a geometry teacher. Anyway, we need to know theta. How do we find theta? Kelsey? Yeah, it's 360 divided by 6 because I could draw this same thing 6 times. So theta is 360 over 6, which is 60 degrees, which is also pi over 3 radians. So I can find the area of one segment and then just multiply by 6. And that's all we have to do. So let's find the area of the sector. 1/2 theta r squared in radians. So 1/2 pi over 3. And our r is 4 squared. That's 16. What is half of 16? 8. So the area of the sector is 8 pi over 3. That's one sector. Hold on. Whoa, 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 whoa. We're going to find the area of the segment and then multiply by 6. Okay? Now let's find the area of the triangle. I don't feel like writing the word triangle. I'll just put a little sub-triangle shape. 1/2 AB sine C. That's 1/2. Both our A and our B are 4s again. And sine of 60 degrees or sine of pi over 3, whatever, that one's a special one. We could evaluate that one by hand. In fact, we already did today. I'll just go ahead and draw it again, though. Throw that 60-degree reference angle on there. Nope, 60. Sine is y over r. That gives me half of 16. You guys have already said half of 16 is 8. 8 times root 3 over 2. Oh. Well, what's half of 8? 4. So this is 4 root 3. That's the area of the triangle. 4 root 3. The area of one segment then. The exact area is 8 pi over 3 minus 4 root 3. That's one of them. And we have 6 of them. Yes? So the shaded area is 6 of this. This is an exact answer when you distribute the 6. Oh, but look. This 6 over this 3 turns into a 2. So it's actually 2 times 8 pi, 16 pi, minus 24 root 3. Oops, I forgot my 4. That's the exact shaded area. I just distributed the 6. But then, of course, I'm going to have to grab a calculator to figure out what that number is, because I don't know. 16 pi minus 24 square root of 3 is... Oh, and if you round that to 2 decimals, you actually get bumped up to 8.7. Boom, baby. There it is. Guess what, folks? You're done learning Algebra 2 this year. Woo, you did it. Congratulations, nerds.